Testing on Twitch. Testing on Twitch. All right, Twitch works. Let's try YouTube. Testing on YouTube. YouTube. Hello. Testing on YouTube. Testing, testing. Okay, YouTube works. Testing on X. Testing on X. Testing on X. Testing on X. Testing. Audio. YouTube. Yep. All right. There's like a lag with the live on X. It's not actually live. How's it going, Oma Viva? How's it going, JohnBoy01? Harrow? I don't know what Harrow means. How's it going, Sarah? All right, let me take a sip of water and get this started. All right, welcome everybody to another Who Post stream. Today we're going to be looking at voice mode. So voice mode is obviously the name of OpenAI's latest release, which is basically a speech-to-speech experience where you're talking to some kind of LLM and it's talking back to you in audio form, and you can kind of interrupt it. It's more naturally in the speech modality, but we don't have access to any information behind that. So instead, we're going to be looking at two very, very conveniently released open source papers that are effectively the same thing. So we have Moshi, a speech text foundation model for real-time dialogue. This paper came out on the 18th of September, 2024, so not too long ago, just a couple weeks. And this is basically coming out of this organization, QTAI? QT? Is that what they want? Like cutie? But QT is just a small little squad. This is their X or Twitter profile. So you can see Paris, France, about like a dozen people here. Pretty tiny little lab, but you really got to give them credit because this paper is very extensive. It's, look at this, over 67 pages of literally everything they did, all the experiments they ran, all the comparisons, ablations, every single like part of their architecture, how they came to that, the reasoning behind it. It's a very nice paper, and I really appreciate that there's people in the open source community going out there and choosing to release that. You know, it could have been very easy for these guys to keep that private. I'm sure the VCs that invest in them even told them to keep it private, but the fact that they're choosing to make it all public, you got to give them credit for that. So open source, closed AI obviously being the voice mode out of GPT, and then open source being these guys. So go ahead, give them likes, follow their page or whatever, you know. It's the easiest way to support these types of things. The other paper we're going to be looking at, also similar release date, called LLaMA-Omni, Seamless Speech Interaction with Large Language Model. This coming out of a couple different Chinese academic institutions. I don't know, Key Laboratory of AI Safety. Is that like an academic institution, or is it like a straight up government institution? I don't exactly know. But basically the same thing, right? Speech to speech, but with a slightly different design. So we'll get into it once we actually get into the nitty gritty, but these have slightly different designs that result in slightly different experiences. So we're going to start with the abstract of the Moshi. So going Mark B, Ed, Aries, Majetti, Sotaki. All right. Current systems for spoken dialogue rely on pipelines of independent components, namely voice activity recognition, speech recognition, textual dialogue, and speech-to-speech, which cannot emulate the experience of real conversations. Because the problem is that the current speech-to-speech systems that you've interacted with, up until pretty much these and voice mode, are generally made by concatenating a bunch of separate little bricks together, right? So you have an ASR, which is something that's taking your audio, turning it into text. Then that text is being fed into NLU, which is just a really old way of saying LLMs, basically, a text-to-text model. And then you'll have a TTS, or text-to-speech, that then takes that speech and then turns it into, or it takes that text and turns it into speech. So the combination of those three systems is pretty much what people have been relying on, especially because there was already well-working systems that did ASR and well-working systems that did TTS. And then as soon as LLMs came in, it kind of became very natural to combine all three of those together. But the problem is that latency compounds along the many components of these pipelines, resulting in a typical global latency of several seconds, right? So by the time you finish saying what you're saying, and it goes through the ASR, and then it goes through the LLM, and then it goes back to the TTS, it's like multiple seconds, right? And that really is just too slow for humans that want that kind of natural conversation feel. And also, paralinguistic information, such as emotion and accent to non-speech audio, are lost. Right? So basically there's no emotion there. Like anything that you say gets turned into text, and then the language model doesn't have this kind of notion of like intonation or emotion or like the timing or anything like that. It's just kind of robotically producing speech from the text. Okay. So Moshi, as well as this LLaMA-Omni, are both going to try to solve that by basically baking all these parts together, right? So they're going to combine what used to be these three separate systems of the ASR, LLM, and TTS into kind of one system, which still is transformer based, but kind of does it in this novel way that they call the multi-stream. So this is the Moshi, which is two pieces, but we'll get into that later, is the first multi-stream audio language model, a model that explicitly processes the input and output audio streams jointly into two autoregressive token streams. This altogether removes the concept of speaker turn and thus allows training the model on natural conversations with arbitrary dynamics, including overlap and interruptions, right? So there's no longer this notion of like, I'm saying something, then you're saying something, and then I'm saying something, and then you're saying something, right? Which is really the way that language models work in general, right? Any kind of text-based language model, it's autoregressively producing tokens one at a time. So whenever you're talking to a language model, all the tokens are in the sequence, right? So it's like there's a discrete stopping point between when you stop inputting tokens, and then the model starts outputting tokens, and then these are your tokens, then the model's tokens, your tokens, model's tokens, right? There's kind of an explicit single stream that only allows for this one person talking at a time. But in Moshi, they now have two streams, and they actually have more than those. They're going to have a couple different sequences, but they're both happening at the same time, which means that there can be overlap, right? Which is something that happens all the time when you talk to a human. You're kind of constantly overlapping a little bit, like you interrupt someone, and then they'll stop, and then you can keep talking. I think the way they describe it here, I think, wait up, we're going to be bouncing around here for sure, but... Okay, maybe I'll stop. Let me just read through this paper as is, because sometimes I try to like bounce around too much, and I spend half the stream just kind of like searching for some random highlight that I had. So let me just go through this in a more natural way. All right. Generates speech-to-speech generation. The model generates speech as tokens from the residual quantizer of a neural audio codec. Right, so obviously there's going to be a neural audio codec in here. Let's see if I have a image of this pulled up so you guys can see this, right? A neural audio codec is just your standard image encoder, image decoder, anything that has that code word in it, right? Like at the end of the day, what are you really doing? You're taking some high dimensional, or in this case, an audio waveform, which has a lot of little samples, right? It's sampled at maybe 24 kilohertz. So there's a lot of little individual numbers representing the amplitude of the basically pressure wave in air that represents air, or that represents sound, right? And that's a lot of information. It's kind of annoying to use that much information, so you want to compress it, right? Specifically for feeding into a transformer, it needs to be compressed into a discretized sequence of tokens. So largely what these neural audio codecs are is two models, right? One encoder, one decoder, one thing that takes your audio waveform and then compresses it in a lossy way, right? So it's losing a little bit of information, but you're getting a whole lot of compression out of it, right? And in this case, you see how it's turning it into these little tokens in a sequence, right? And then your decoder, which is going to be a different model, but is going to take a sequence of tokens and then turn it back into an audio waveform. So like this is what your computer needs to actually produce sound, and then this is what your computer is hearing from the microphone, right? And then these neural audio codecs are basically just converting these raw waveforms, which is kind of like the physics of sound, into a sequence of little tokens that you can then feed into an actual language model, right? Or transformer, because the transformer needs the little discrete sequences of tokens. Okay. It models its own speech separately from that of the user's speech, right? So it's doing this multiple parallel streams. It's not just one stream, one sequence. It's going to be multiple sequences in parallel. It's predicting time-aligned text tokens as a prefix to audio tokens, and it also has this idea of an inner monologue. So I do have it pulled up here. I don't think we're going to be able to get it to work. I was trying to mess with the like microphone input and like toggling between the microphone input and this like window audio input, but you can very easily recommend this or play with this yourself. Go to moshi.chat, you put in your email, and then you just go right here, and
Hello.
there you go.
What's going on?
I don't think you can hear me, but can you hear me?
I can hear you.
I can hear you? All right.
Seems to be the
can
issue.
you guys hear this? I don't know if you guys can hear it. No, I don't think you guys can hear the output. But this little text right here is the inner monologue, right? But the inner monologue is not like that's exactly what it's
sense your
outputting, right?
thoughts.
So the inner monologue
It's
is basically
not
just
that
like almost like a little
I am
scratch
doing
pad
my best
where
here.
it can output text, and then that's an additional stream, right? So there's
I
actually
understand what you're
many
saying.
different streams here.
Yes, I can
here
see
you can
it.
see, for example, here there's a lot of these figures in this paper.
I am aware
Where you can
of
see that when it says it's multiple simultaneous streams, these are the multiple simultaneous streams, right? There's a bunch of
I
them.
get that too.
And one of them is going to be the text tokens. Another one is going to be the semantic tokens,
Right.
the acoustic tokens, the semantic tokens. So the text tokens are going to be the inner monologue. The semantic tokens
can
are going to
do
be
that.
tokens that represent the content of the audio. Acoustic tokens are the kind of actual waveform kind of tokens that represent kind of how this actually sounds.
And I understand
And then
that.
it's also modeling the user stream as well, right? So maybe we should look at this figure. We're kind of jumping ahead by
can
looking at
see
this figure,
that
but I think it's a nice demonstration of what exactly they mean by this multi-stream situation, right? So
I can agree with
here you
that.
have your robot, which is this, right? This is the Moshi. Let's disconnect so we can give somebody else a chance. And you can see how it's saying, hello, I'm Moshi, right? And you see this orange, this corresponds to hello, right? Here's the text tokens, right? And we're going to see that there's something interesting that you have to do here where because a text tokenizer, specifically they use the sentence piece tokenizer, I'm pretty sure. They mention it somewhere over here. Okay. I don't know where they mentioned it, but the sentence piece tokenizer, right? It's breaking up this text right here into tokens, and the way that it breaks it up, right? Generally, for example, this word "I'm" is actually split up into 3 tokens, into this leading space I, this little apostrophe thing, and then M. So there's kind of an unfortunate reality of these LLM tokenizers that the word I'm, even though it takes basically less time to say than the word hello, actually gets tokenized into more tokens than the word hello. You see how the word hello, comma, is just basically 1 token? So that's why they had to introduce this idea of padding tokens. So we're going to get into that later. But you see how some of these are pad token, pad token, pad token. That allows because all these streams are kind of being somewhat synchronized, right? You want there to be the ability to say, okay, even this word doesn't take that long to say. Therefore, even though it's a lot of tokens, this one here, I can have it take longer to say, even if it's 1 token. I don't know if that made sense for people. Okay. You can hear the output. Oh, okay, pretty cool. I would definitely recommend you guys try it out. All right. But you see here how the orange tokens are the word hello, then the yellow tokens are the word I'm, the green tokens are the word Moshi, and you see how they're kind of like offset a little bit. There's a little bit of a delay here, right? So it's kind of predicting this entire column is one way to think about it. Like every time step, and each time step is basically 80 milliseconds, it's outputting an entire column of these. Boom, 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 boom. And then you see the hey Moshi that the user is saying are these purple tokens. The first time you start getting those purple tokens is before the green tokens are even done, right? So it's kind of this like rolling window where they all kind of overlap. And whenever the user's talking, right, it's not like Moshi stops, right? So in a language model, right, if you were talking to GPT with text, these tokens and these tokens are all in the same sequence. So like you can't produce acoustic, like semantic tokens from the LLM while the user is producing semantic. You have to decide, is this the user's token or is this the assistant's token? But here, because you're doing this kind of all together, you can have this overlap, right? So whenever you're talking, you're still producing tokens and predicting tokens, except the tokens that you're outputting are basically silence tokens, which is kind of a cool idea. Okay. Which allows for the model to handle overlapping speech turns, right? Where you can, the user audio can be overlapping with the audio tokens coming out of the model. Okay. So sorry about that. I had Moshi going on at the same time. I'm sorry about that. You guys had to listen to multiple people just talking at the same time. That sounds pretty bad. Okay. Let's keep going here. Scalable hierarchical modeling of audio tokens, which can handle several minutes of context while generating audio in real time. This is the related work, right? Fundamentally incompatible with live interactions. The model needs to produce the entire answer as text before it starts speaking. This is whenever you break it up into different chunks. And then they have the inner monologue. The inner monologue decomposes speech into a chain of text, semantic, and acoustic tokens. So there's your inner monologue right there, right? This text right here. I'm doing my best here. I can understand what you're saying. Yes, I can see it. All right, so that's basically Moshi there. Maybe one thing here, the knowledge of its helium backbone. So one difference between, for example, the LLaMA-Omni, right, which is this paper, and this one here, the Moshi, is the LLM that they kind of start from. So in this case, they actually start from this helium language model. Helium is a transformer language model, blah, 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 right? But it's not very big, and I think it's not very smart. So the intelligence of the actual voice assistant is largely going to come down to the LLM that you're starting from, right? So in this case, this helium model is not going to be as smart as this LLaMA model here. So these guys actually use, as the kind of starting language model, they use LLaMA 3.1 8B instruct, which is kind of a small LLaMA, right? The 8B is one of the smaller ones, which generally tend to be stupider. So I think this one actually has a smarter language model than this one. So this LLaMA-Omni is probably slightly smarter than this helium or this Moshi, just because the LLaMA 8B is probably slightly smarter than helium, but that's me just kind of predicting randomly. I don't actually know. I didn't test both of these guys for actual intelligence here. But let's go into the LLaMA-Omni real quick, just so we can get caught up and then go both of these papers at the same time. So LLaMA-Omni, also advertising low latency. It's a pre-trained speech encoder, a speech adapter, an LLM, and a streaming speech decoder. So the pre-trained speech encoder, that's this part here, right? And pre-trained basically means they're not going to be trying to push gradients into that. I think in this one, they do put a little bit more effort. They train their own encoder, right? That's this Mimi here. A semantic knowledge distilled from a neural audio codec with residual vector quantization distilled from a self-supervised speech model. So they're going to be using their own encoder here called Mimi. You see the encoder Mimi here, and then the decoder Mimi there, right? So that's the two halves of Mimi, which is this encoder and the decoder. In this one, they're basically going to use a pre-trained one, specifically the Whisper one. It simultaneously generates text and speech responses directly from speech instructions. The latency is as low as 226 milliseconds. And in this one, we actually get a latency of 160 milliseconds as the theoretical lower limit, and then 200 milliseconds in practice. So with these type of papers, right, where it's all about this like latency, I wanted to kind of really visualize what that's like. So I got GPT-01 to make a little latency comparison website for you. So this is just like I just zero shotted like this little website using GPT-01, but you can see that's what 200 milliseconds is, right? And this is 226 milliseconds. So that's pretty good, right? Like imagine if like blah, 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 and then as soon as that green square flashes, the other one starts. So this is doable, right? And you see in some places like human reaction time is around 100 milliseconds. So, and then for example, 60 frames per second is around 16 milliseconds. So like all we need to get is like one more order of magnitude, and it's way faster than you're ever going to need, right? And like one way to think about it is that if you remember phone screens, there was a point where the phone screens were actually low resolution, and then there was multiple generations of phones where the resolution of the screen kept increasing. And then at some point, the screen resolution was good enough that even if you held the phone like 20 centimeters from your face, more pixels would not make a difference because just the resolution that your eye can even detect is limited at some point. So there's the same kind of thing with latency. So as a human, right, you can tell the difference between something that's like 10 milliseconds and 100 milliseconds, but 1 millisecond compared to 10 milliseconds, and then if you go sub 1 millisecond, like it's not going to matter. So I think we're getting pretty close to like the latency that this is more than good enough, and we don't need to necessarily push on that anymore. Okay. The simplest way to enable speech interaction is through this cascaded system. We already talked about that, right? The ASR TTS, that is pretty much already gone now. LLaMA-Omni simultaneously generates speech and text, right? This simultaneous generation. So both papers have this idea, right? Multiple streams. They're using this non-autoregressive streaming transformer, which predicts the sequence of discrete units corresponding to the speech response. The LLM autoregressively generates the text response, and then the speech decoder simultaneously generates the corresponding discrete unit. So this one is like a little bit closer to the kind of more classic ASR TTS systems because it is kind of like using this to create that, right? It doesn't have the nice breakdown into multiple streams that this the Moshi has, but the latency is still pretty good, right? At 226 is basically exactly the Moshi latency, so I think it's comparable. Okay. Let me see, can we distill these types of models like LLaMA 3.2 did? Yes, you can use distillation for these, and distillation is a big part of the story for these papers, right? So actually, for example, in this LLaMA-Omni model, right, they're heavily using Whisper Large V3, right? Because the encoder, right, this speech encoder here, right, which is actually what converts the waveform into some compressed representation, and then the speech decoder, those are just Whisper Large V3, right? So they're using Whisper Large V3 as part, like, this research wouldn't be possible without Whisper Large V3. And even though these guys train their own encoders and decoders, right, their own Mimi here, they're still using Whisper Large V3 heavily, right? And not only that, but they're using a different model here. So for example, they use WAV-LM. So WAV-LM is also the same idea, right, of like taking audio, compressing it into this little lower dimensional representation of that, and then uncompressing it with a decoder. It's trained on 60,000 hours, or 60,000 hours of audio, right? And actually, when these guys train the Mimi, what they're actually doing is, part of it is distillation. So this part here, adversarial losses, this is basically saying that when I feed my audio into this encoder and it turns it into this lossy compressed version of it, and then you decode it. This here should be the same as this here. So one easy way to create a learning target and a loss that allows you to push gradients into this encoder and decoder is by comparing this orange to this blue, right? And that's what this is happening here, right? This adversarial loss. You want this to be the same as this. But they have an additional learning signal that is coming from WAV-LM, and this is basically what distillation is, right? So you have the teacher network, which is WAV-LM. You see how it's frozen. They're not changing that at all. That WAV-LM will consume this audio and produce some kind of vector of numbers, right? And what they're saying is, okay, our Mimi model, which we're training from scratch and we're trying to get it to basically reconstruct this as high as possible, we're also going to have an additional learning signal that says, hey, okay, this intermediate kind of bottleneck representation that you have here, it should actually be similar to what the WAV-LM outputs whenever it turns this waveform into some kind of vector. So they are using a distillation loss to create their encoder, right? So that's the answer to your question of like, is distillation used for this? It is used for this. This is not even like original, right? Like they're distilling a different model. And not only that, but we're going to discover later on in the paper that these guys also use Whisper v3. So for example, the data set that they use is they take a bunch of text data and then they get it to talk, right? We transcribe this with Whisper or whatever. So like, I think we'll get into these details a little bit later, but like what I'm trying to get at is that like this type of research is not possible without Whisper, without WAV-LM, without I think they use another TTS model here, Audio SR, right? So basically they're synthetically creating data sets by taking text data sets and turning them into speech data sets. And then not only that, but they're also using some other encoder that somebody else trained and distilling that into their own version of that. So we're kind of getting to the point of AI research where you don't have like one data set and then you train on that data set and then that's it, right? It's like you're using all these other models and data sets that are then being filtered with other models, and right, like there's a ton of pre-trained models being used as part of either the data set creation or directly in the actual training via distillation. So it's like all of AI is really this giant ball of everything being interconnected, because at some point someone's going to do exactly the same thing with this, right? Someone's going to start using Moshi in some way to create a gradient to push into their own model, right? So it's like all the models are kind of just all feeding off each other's outputs, and that's how the kind of the future is kind of going forward. Everything is becoming interconnected. In some way, Whisper is being used for this, right? And in some way, this will then be used for some future version of Whisper. Padded to fit a timestamp. Can it generate the text before speech for intonation? Yeah, the intonation is part of the acoustic tokens, right? So they're kind of separating it out into what they call acoustic tokens and semantic tokens. Semantic tokens is going to be like the actual knowledge or like content of the actual word. So like the word hello, right? There's some association of like it's a greeting and like it's something you say and like blah, blah. So like that is the actual semantic token. And then the acoustic token is like how you actually say the word, right? So they're separating those out a little bit, but the model that is generating all of these, right, column by column by column, has access to all of these streams, right? And that's, we're going to look into that later, but it's this depth transformer, right? What they call the hierarchical transformer. Okay. We were reading, this is what we were reading. Okay. So we're back into the LLaMA-Omni paper, right? They have their speech encoder, which is encoding the speech that's coming in from the user. So you have some speech that's coming in from the user XS that's being encoded, and now you have a sequence of speech tokens H, right? Those speech tokens H first need to be downsampled because there's too many of them, right? And that's what they're doing there. They're concatenating them in order to downsample them. And then they're taking a speech adapter. So the this design is actually very reminiscent of vision language models, right? So a lot of vision language models, the way that they're designed is they basically have some pre-trained image encoder, and then that pre-trained image encoder, they have to glue it into a pre-trained language model. And in order to kind of glue it to this pre-trained language model, they create this kind of adapter or projector. There's different words for those, but what it really is just a 2-layer perceptron with ReLU activations, right? So it's like a linear layer that consumes the downsampled speech tokens from the pre-trained Whisper v3, and then a ReLU, nonlinearity, and then another linear layer. So really, this is almost the same as the vision language models, right? The open source vision language models like Lava, this is very similar design, right? And also has the similar 2-stage training process where in stage 1, you have your frozen speech encoder, which is your Whisper, right? And that's frozen, which means you're not pushing gradients. And then you have your language model, which is your LLaMA, LLaMA 8B, and your speech adapter, which, right, and you need to initialize basically from scratch. So the first part of training, right, this stage 1 of training is just getting the speech adapter and the large language model to understand each other, right? So this large language model, this LLaMA 3.1 8B instruct, it doesn't know what the fuck these S tokens are, right? These speech representation tokens. Like, it's never seen that before, right? So it needs to receive gradients in order to understand what these tokens are. So that's in stage 1, what you're really just doing is gluing the LLM and the speech encoder together. And then in stage 2, now you freeze those. So you see now you've frozen the language model, you've frozen the speech adapter, you're no longer pushing gradients into those, and really you're just getting this output to be good, right? You're getting the speech decoder to, rather than understand the tokens that are coming out of the speech encoder, which is how it was trained, right? Normally this decoder during training, it's just, which in this case it's Whisper, right? It knows how to take these tokens here and turn it into a waveform. But you need to modify it now. You need to push some gradients into it so that it can understand the tokens that are coming out of this LLM, right? Because they're going to be a little bit different than the tokens that are normally coming out of the speech encoder. Okay. LLaMA 3.18b is the LLM, right? And all its basic, this is just kind of standard language model stuff, auto-regressively generating, right? Which means it's just generating one token at a time by looking at all the previous tokens, and trained using a cross-entropy loss, which basically just means that you have a vocabulary of all possible tokens or a dictionary of all possible tokens, and then it's saying, okay, with this, here's the probability of each individual token being the token that I'm going to produce next. And then usually I just pick the one that is the highest probability, or maybe you have some fancy temperature type of stuff to more randomly pick a token, or yeah. What is WebLM? I don't know. WebLM sounds pretty generic. There's probably multiple projects that are called WebLM. If we keep using other open source models as a teacher model to cross-check and adjust gradient, do you think we will make a good significant progress? Is it like a loop? Yes, 100%. So, Sid, this is kind of what I was trying to say, is that we're like, it's all like, you know that part of the sci-fi movie where they're like, the AI is improving itself, right? We are literally living that. This is exactly what that looks like, right? AI improving itself doesn't mean you have like some giant like like generic like Rehoboam style like AI sitting there like writing its own PyTorch code, right? That's not what AI improving itself is actually going to look like. What AI improving itself is actually going to look like is more like these papers, right? Where, hey, how did we make this paper? Well, we took a pre-trained language model and then trained it using and then used a pre-trained speech encoder, and then used a data set that we created by taking some Wikipedia articles and then turning them into speech by using this other pre-trained speech encoder, right? So it's like you're using a bunch of other models to either create the data set or provide a distillation loss or in some way create your model. And then that model, which is going to be currently the best, right? I think these two are probably the state-of-the-art open source speech-to-speech models. Those are going to then be used by some other group in the future to also maybe generate some data set or provide some kind of distillation loss. So it's like that is how the AI is improving the AI, right? Is because you would not be able to do this if you didn't have Audio SR. You would not be able to do this if you didn't have Whisper Large v3. So it's all becoming this interconnected mess, right? All AIs are really just the same AI because they're kind of being fed from the output of other AIs and so on. I wish I had a better way of like explaining that, but it's kind of like a nebulous concept to explain, I suppose. Question from They Call Me Ken. Do you know if any of these models can use the CMU pronunciation database? I mean, I don't really know much about the CMU pronunciation database, but I'm sure there's some opportunity to use other data sets for this. Speech input has different characteristics compared to text input. So in order to take a text data set and turn it into a speech data set, you have to add appropriate filler words, such as hey, so, convert non-text symbols in the instructions into their corresponding spoken forms. Existing responses from text instructions are not suitable for direct use as speech instruction responses. So text-based interactions, models tend to generate lengthy responses using complex sentences and possibly including nonverbal elements like ordered list of parentheses, right? Which is another reason why the more kind of classic ASR, LLM, TTS stack was never going to work, is because the LLMs that are producing the output there don't actually even produce spoken English. They produce like written English, right? And these guys are basically saying there's a big difference between spoken English and written English. So part of what they're doing here is after obtaining the instructions and responses, we convert them into speech using a TTS model, specifically Cozy Voice 300M SFT. So they're taking these instruction tuning data sets, such as 50K instructions from the Alpaca data set, right? So the Alpaca data set is like an instruction tuning data set, like this Ultra Chat, which is basically here's a question, and then here's the response, and then here's a question, and then here's the response. And they're taking that text data set, they're kind of adding in filler words and making it more of a spoken English rather than written English, and then turning it into a speech data set with a pre-trained Cozy Voice 300M SFT, right? Randomly selecting either male or female. So it's like all of these audio models are basically trained on text data that has been turned into speech data, which is kind of interesting because I wonder if you could do that for vision too, right? Like this, imagine if you had like descriptions on Wikipedia, and then you take those descriptions, feed them into an image generator, and turn that into images, and then train an image model on those images, right? Or I think this works with audio because audio is, the quality of synthetically created audio is much closer to real audio, right? Versus right now, the quality of synthetically generated videos is not quite the same as real videos. So there's a little bit more of a sim to real gap in video and image creation, but I feel like in audio, there is very little to almost no sim to real gap, right? Which is why both of these papers effectively synthetically create their chat data sets. And it works pretty well, right? So 20,000 hours of synthetic speech data. To give Moshi its own consistent voice, we also conditioned the TTS on the voice of a single actor who recorded monologues covering more than 70 speaking styles. So pretty complicated, right? They're taking this instruction tuning data set, turning it into an audio data set, and not only that, but the TTS that they use to generate that synthetic audio data set is then fine-tuned on some specific dude talking in 70 speaking styles that they paid for, and then so that TTS will now produce audio that sounds like this one guy. Or I guess it's probably a girl, right? Because this is a female audio. Okay. We were getting carried away. We were talking about this paper, fine tuning. We were looking at the LLM and then the speech decoder. So the speech response, blah, blah, blah. We use a pre-trained Hubert to extract continuous representations of the speech and then convert these representations into discrete cluster indices using a k-means model. So that they're talking about this, the fact that at least in this LLaMA-Omni, it's effective. The decoder is basically saying, okay, here's this audio or this text, and then I'm going to turn it into audio. So it's a little bit of a simpler design than what they're doing here in the Moshi, where you have like the semantic, all of these tokens are all kind of like mashed a little bit more closer together, which allows for kind of more information to flow between them versus something like this. You're really just, because it's a little bit more separated, you're kind of more, I think, relying on the quality of the decoder, which is probably why they have to push gradients into this, right? That's something, I don't know, maybe I'm right, maybe I'm not. Okay, but the speech decoder. you have the final discrete unit sequence YU, blah, 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 blah. K is the number of clusters. L is the length of the discrete unit sequence. So K is the number of clusters basically means that what's coming out here, there's a limited, you could think of them like tokens, and really what you have to decide which of the K clusters you're doing. So it's almost like the kind of code book or dictionary where there's like a discrete set of possible things it can be. In this case, each of the things it can be is like the center of one of these clusters, and then it's going to pick which of those it is, right? So each YI that it outputs, right, where I is from length 1 to L, so the length of the sequence is L, right? And for each of these Ys, it's one of these possible values, right? So it's in the set of 0 all the way to K possible values. The discrete units can be converted into a waveform with an additional unit-based vocoder, right? So now we're back to this exact same. You have some discrete sequence of things of which each thing is one out of K possible things, and then this decoder is just saying, okay, I'm going to take that stream of things and then turn it into the actual waveform, which is actually what my computer is going to output. To generate speech responses simultaneously, we had a streaming speech decoder D, which is just several transformer layers. The speech decoder runs in a non-autoregressive manner, which takes the last output or the output hidden states from the LLM as input and generates the discrete unit sequence corresponding to the speech response. And this is kind of important because this is going to fundamentally limit what LLaMA-Omni can do, right? Because this one here, it's producing the acoustic tokens, and so the actual audio that's being produced has an ability to pay attention to everything in the conversation, right? So if you were talking angry and you were telling it to talk angry, right, it would have that context and it could pay attention to the fact that you were talking angry. So when it produces the next audio tokens, it can actually say, okay, these should be angry audio tokens. Versus this one here, it's not autoregressive, right? So it's basically just taking the chunks and then one at a time taking those chunks and turning them into audio. So the fact that it can't kind of pay attention to the entire context, I think, will limit the capabilities of this speech-to-speech system. Okay. Output the hidden states, upsampling. A lot of upsampling and downsampling in these papers, right? Just because like audio is just too many samples, right, per unit time. So you really need to reduce it down into a smaller or sequence so that these LLMs or these transformers can handle it. Blah, 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 hidden state. So this is how they're actually getting the actual output of the audio. We apply the collapsing function and fed into the vocoder to synthesize a waveform. But effectively, it's just you're picking the best one. We select the best alignment. So like effectively, whatever's coming out of here, right, you're doing this K possible values, and then you're picking the best one out of those, and then your vocoder just says, okay, here's the token, then here's the sound that is associated with that token. Okay. I think we did that, and then we got to the data set. So let's go back to this one here. Let's read into the details for this one. Okay. This paper's so long, right? There's so many things here, so many details, and I really appreciate that they gave all these details. Okay, so we were looking at LLaMA-Omni, which is the wave, which has this encoder decoder, and then they have to train this adapter very similar to a vision language model, right, using a pre-trained large language model. Okay, so now we're back in the Moshi, and they have, rather than using the encoder decoder of the Whisper, they make their own, which is Mimi. Is that supposed to be like Mimi like Mini or Mimi like Mimi? I don't know. A neural audio codec combining semantic and acoustic information into a single tokenizer by using residual vector quantization and knowledge distillation, right? The distillation there is coming from this other model, the WAV-LM. The depth transformer compatible with streaming inference. Depth transformer actually comes from this here. So we'll give those guys a star. This is depth transformer. Here it's called the RQ transformer. This is from Lucid Reigns. This guy actually is a little bit of a Twitter celebrity. RQ transformer, which proposes a more efficient way of training multidimensional sequences auto-regressively, right? So basically this is just a transformer that can deal with multiple sequences. So it's not like an LLM that's just producing one sequence and consuming that one sequence auto-regressively. This is like, it handles multiple sequences because you're going to be separating out the acoustic tokens, the audio, the semantic tokens, and the text tokens or inner monologue tokens, right? So you have to be producing all of those at the same time. I think we're here. Novel, and then we got to here. Language audio modeling. I think we already did that. Then we got here. The main components are the text language model backbone, this one here, which they have to kind of... The tokens that go into here are so weird that that's why they kind of have to train this in such a custom way, right? And because it's also... So that's why I think this Helium is actually kind of a pigeon brain. I think the whole Moshi is probably going to be kind of stupid because it's just like dealing with such a weird modality and like having this kind of custom architecture like that. I just don't imagine this is going to be able to, like, you're very quickly going to have this catastrophic forgetting problem where it just like stops actually knowing what to, like actual knowledge, and it just kind of only gets good at producing this audio crap. So they actually talk about that too as well, where during the training they actually have to basically alternate. Yeah, we randomize. Here we go. To prevent catastrophic delay or forgetting, we also train half the time on batches of text-only data, right? So the problem is that when they're training this model here, this Helium, when they're pushing in batches of training data that is basically this audio shit, it's going to kind of start forgetting the information, such as the Wikipedia, all that, like the actual like knowledge information. So they have to effectively change in and sometimes start putting in kind of just only text data so that the model doesn't become kind of stupid over time by catastrophically forgetting all the original information that it received in the original training, original pre-training. Okay. We're here, Helium language model. What is the actual source of this? Based on the transformer architecture, flash attention, sentence piece. So this isn't pre-trained. They like train this all themselves. Yeah, this is from scratch. Is Lucid Reigns even on Twitter? Is he not? I feel like I've seen this guy. Maybe not, dude. Maybe, like, because I went to this repo and I looked at it and then I was like, holy shit, wait a second, I'm already following this guy. So that's kind of why I say he's a celebrity, because it's like, this is, look at this dude. This guy grinds. Holy shit. It's been grinding since 2011. Maybe not. When did he start grinding? Oh, there we go. Starting, boom, 2018. You can see he's not working on the weekends. He's just working during the weekdays. Here he was maybe... Sometimes you can go into a company and they don't... You use a different GitHub or you're not like committing. So the GitHub commit graph is not indicative of necessarily how hard you're working. But then you go, boom, right around 2019. This is when he was like, fuck it, I'm working weekends. So you see that? He's working on Saturdays. He's working on Sundays. And then he basically just perma works. Took a little summer vacation right here. Here's a little Thanksgiving vacation. Here's a little summer vacation. Oh, there's a little March break. All right, we're going to stop creeping on this guy's GitHub. Training of Moshi goes through 4 phases. Pre-training on unsupervised data. Post-training with simulated multi-stream. Fine-tuning on the Fisher dataset, and then instruction fine-tuning on a custom dataset. During the pre-training phase, we keep training half of the time on full text batches using a separate optimizer state. So they're kind of like pushing gradients from 2 slightly different things just to prevent this catastrophic forgetting situation. Audio tokenization. Let's get into this. Okay, the encoder projects a single-channel waveform X to a latent representation encoded X by cascading residual convolutional blocks that interleave dilated and strided convolutions along with ELU. Okay, so what they're saying is this single channel waveform X in R of L, that's basically saying that this signal here, this waveform, is just one channel. You can have 2 channel, right? 2 channel means left and right audio, but for something like speech, like left and right audio doesn't make a ton of sense, right? You can just have that one channel and it reduces the total number of channels. And it's just one number, which represents basically the amplitude of this wave, right? So that's this single channel waveform X. And you're going to turn it into this encoded latent representation, which is now S by D, right? Which has, okay, there's some dimensionality D, and there's going to be S of these little tokens there. Or S is the length of the sequence, and then D is how many of those there are, right? So D is kind of the width, I guess, and then S is the length. We add transformable modules in the bottleneck, one right before quantization, one right after. 20 seconds of total context. They do have this interesting point here that they said later. Mimi is causal and can be used in a streaming fashion, both for encoding and decoding. The overall stride corresponds to 80 milliseconds, given that a first audio frame of 80 milliseconds, Mimi outputs a first latent time step, which can be decoded to 80 milliseconds of output. So the entire Moshi, like each column, like everything is moving at this 80 millisecond, basically frame rate. And we can go in here and we can type that in. This is 80 milliseconds. So the time between I hit the button and then the thing flashes, that's 80 milliseconds. That's how long each of these columns is, right? So it's 80 milliseconds, 80 milliseconds, 80 milliseconds, 80 milliseconds. And that actually is where they get their theoretical latency. So later on here, they mention, I think in this one here, no. Where is the latency? Latency calculation. Right here. Yeah, so introducing a delay of 1 to 2 steps greatly improves the quality of the generation. A slight delay between the semantic and acoustic tokens. So that's this 2-window delay, right? So they have like this 2-window delay, and 2 times 60 milliseconds, which is what they're saying here, is 160 milliseconds. So whenever they say a theoretical latency of 160 milliseconds, that basically means that this whole thing is running at this frame rate of 80 milliseconds, and we're introducing a 2-frame delay between the kind of input and the output, just so it can have a little bit more context, right? Like they could have squashed these more together, but if you wait a couple frames, then you're going to have extra frames. So like if you wait to produce this token here, right? Imagine if you had to produce this token here, right? Then you would lose all the information that you could have possibly had from knowing what these tokens are, right? So by introducing that kind of like 2-frame delay, you're allowing more relevant information to kind of flow into it. And because we're so close to human perceptual anyways, right? Like the difference between 80 milliseconds and 200 milliseconds is not enough to make a qualitative difference in the experience of the user interacting with the system. So if you have a frame rate that's smaller than that, go all the way to the limit so that you can get the maximum possible information to produce the most highest quality next acoustic and semantic tokens. Damn, you guys are popping off here. Why does Notebook LM's podcast feature it using like the same approach at all? Or they haven't undisclosed it? All the things sound authentic and not real good. So I do actually have that pulled up. So Notebook LM, so this is a question by Sid, is a recent experience, I guess is the best way to describe it, that Google released. And you can just go there yourself. If you type notebooklm.google, you can go on there. And you can upload any amount of stuff, and I just put in both of these papers. And then you can effectively ask questions about the papers. You can ask for summaries of the papers, right? So like you can, close chat, you can like, here's a summary of both papers. Here's a quiz with answers for both papers. But the feature that everybody's loving is this one here, is the fact that you can create a audio, like a podcast. And it's kind of interesting because it's like an actual podcast. It's like 2 people talking to each other. This is not using these type of architectures. I can tell you that right now, because these architectures are all about basically like the latency, right? They're all about instantly consuming audio from the user and then being able to use that to produce audio in as quickly as possible, right? So it's all about like reducing that latency so you can create a conversational experience. But these guys don't give a shit about that, right? This is like, it creates the whole thing at once. So if I had to guess, I feel like this is probably just your classic text into... It's probably a language model with some prompt that allows it, or maybe it's fine-tuned so that it can produce these kind of conversations, these podcasty conversations, right? With all the little quirks that they describe here, right? Like, come on, load. All the little quirks like filler words and blah, blah, blah. And then it just takes all of that text and then converts it into an audio file. So I don't think this is being like generated by something similar to that. Okay. What is my opinion on this? I honestly, I feel like this is not that great because the podcast that it produces is a little bit cringe. It's like it's all fluff, you know? It's just two people talking, but like almost like 90% of the tokens that they're saying are basically just fluff. Like, wow, that's amazing. You know what I really think about that, right? If you were to actually write out that entire podcast and you were to just highlight all the parts that are conversational fluff, it almost feels like the entire podcast is just conversational fluff, right? I feel like, at least when I listen to podcasts, I prefer podcasts that are kind of more information dense, get more kind of nitty gritty, more detailed, rather than just kind of like a we're hanging out and chilling podcast, which is very much the vibe I get from this one. It's like kind of like a we're hanging out and chilling podcast, but it's like, if I want a podcast about papers, it's like I want something a little bit more detailed, but I don't know. That's Notebook LM. That's my, I guess, 5-minute review of Notebook LM. Aren't most podcasts like that? Yeah, and I mean, just to be self-aware, like my YouTube channel is effectively kind of like that, right? Like realistically, like is listening to my summary of these two papers, isn't that really just kind of the same thing here? Right? I'm basically doing the same thing. I'm taking these highly detailed, highly technical papers and producing 2 hours of audio that is less detailed and less technical, right? Because I'm using more kind of colloquial jargon, right? So I wonder if I wonder where that goes, right? Because we now have the ability to very easily generate audio from text. So historically, there's a kind of a separation between spoken English and written English. But part of that separation was because you have to go through a person to create spoken English. But now I feel like if we're going into a world where you could be listening to AI generated audio, like 99% of the audio that you listen to is AI generated, it doesn't need to be spoken English, right? You can now live in a content bubble where all the content you consume is very technical written English that is just turned into spoken English. So I wonder if we'll see kind of like almost like a bifurcation of like English language into kind of like this casual conversational spoken English, and then this kind of more technical version of spoken English that is used to kind of like try to maximally send information from one thing to another thing. I don't know. I'm getting a little bit high level here, maybe. Most podcasts. Okay. Did I watch the LLaMA 3.2 demo yesterday? Yes, I did watch the LLaMA demos. Pretty good. I did consider doing the LLaMA stream, but there wasn't as many... there wasn't really like as much content, right? I figured these two papers, going deep into these two papers and getting a much better idea of like exactly what these speech-to-speech models are doing, at least right now, that felt like a little bit better of a use of time. But I am actually fine-tuning the LLaMA 11B vision model right now as we speak. Okay. The 1B and 3B look delicious. Yeah, the ones that can run on like cell phones. Definitely pretty exciting. All right, let's get back into this one here. So we have the encoder, which is basically distilled from WAV-LM. And they had this transformer. Mimi is causal. We looked at that. The frame rate of basically 80 milliseconds. The context of the transformers is limited to 10 seconds, which still seems a little bit short. You know, we're still kind of context window limited for these audio experiences. We use Q equals 8 quantizers with a codebook size of NA 2048. So basically Q is like the you could think of it kind of like the level of resolution or detail that you're using when you're doing this lossy compression here, right? When you're taking your thing and coding it and then taking your thing and decoding it, the higher that Q, right, basically just means the more layers of residual vector quantization where you're quantizing the residual of the previous thing. So a higher Q will basically make this less lossy, but at some point you're going to pay for it by having just more shit to deal with. So like they choose Q equals 8, which is basically this ... here is like how many Qs do you have? So here you see 3, but in practice they're using 8. Okay. 100 steps per second of audio to generate English speech can be represented with around 3 to 4 text tokens per second. So they have multiple subsequences, VSK, right? This is this RQ transformer. The reason they have to do this, and they have this depth transformer, is that they need to basically consume this entire column of shit, right? They have multiple sequences, and this RQ transformer allows them to consume and produce multiple sequences at the same time, right? And these subsequences, that's each of those things. And they actually have a detail specifically. Here is the sequences specifically. So the first one is just the text. The second one is the semantic tokens. Then you have Q delayed acoustic tokens. Then you have semantic tokens of other, which is the speaker, and then you have the delayed acoustic tokens of other, which is the speaker, right? So you basically have text tokens, which is the inner monologue, then the semantic and the acoustic tokens for Moshi, and then the semantic and the acoustic tokens for the human. And actually, one interesting thing that they say here is when the user speaks and Moshi stays silent, actually, let's go through both of these. In an application setting, prediction for the audio coming from the user is actually ignored as the actual user audio is used instead. However, modeling the user stream as output allows generating simulated dialogues. Okay, so what they're saying here is that when you're going to be, you want to be able to generate conversations between two Moshis, right? And in that type of situation, you basically need to create these purple tokens and these down here, the Moshi tokens as well. So the depth, this RVQ transformer here, or RQ transformer, is actually predicting these purple tokens. So as you're talking to it, it is each little 80 millisecond frame. It's actually kind of almost predicting what you are about to say, right? So that'd be kind of really cool to listen to, where if you had a conversation with this and then you suddenly blocked it out and allowed this to be outputted, you could almost generate a conversation with you talking, right? But when you're actually running this model in inference mode and talking to it, they basically cut that part out. So even though it's generating it's in a sense predicting what you're about to say, that part is basically pipes out into nowhere. When the user speaks and Moshi stays silent, the corresponding audio tokens for Moshi's stream decode into natural silence, a near silent waveform. And the fact that it's near silent is kind of creepy in a weird way, right? It's not entirely silent. So these gray tokens here, these are silent. So it's still outputting tokens, but they're silence tokens, which is kind of cool, right? So it's when you're talking, it's not like it stopped talking. It just now is talking in silence. And I was like, why don't we do that in robotics, right? Like I'm kind of like instantly in love with this weird paradigm. And I'm like, why don't we, let me see where I had that written, but here, Jesus. Let me just talk about it here. So right now, robotics is almost in this state right here, right? Where we have ASR, TTS, and an LLM, right? You still see this modular design for robotic systems as well, where you're kind of producing one stream of action tokens, or like you're consuming a thing and then you're like, but I think this multi-stream design would actually work very well for robotics as well, right? Imagine if you have a streaming transformer like this that is consuming speech tokens from the user. It's also consuming visual tokens from all the different camera sensors, and it's outputting visual tokens, and it's also outputting action tokens. And sometimes those action tokens, the same way that here they correspond to silence, right? You could have action tokens that correspond to no motion, right? So effectively, the robot is always moving. Every 80 milliseconds, there's always some motion command, but that motion command can be like a sit still command. I don't know. Maybe that's not interesting for non-robotics people, but I really like this design, and I feel like we're probably just 6 months away from someone taking this multi-stream design and then using it in a robotics use case, which I think is also perfect because it's like you have multiple streams of input, right? You have the cameras coming in, you have the force sensors, you have the proprioceptive information, you have the speech coming from the user, which is coming from... There's so many different streams of input, and you also kind of want multiple streams of output. So I really like this design for not just audio, but like potentially other use cases as well. Here's your sentence piece tokenizer, right? Your sentence piece tokenizer, as I was saying before, it's really not designed for audio, right? The fact that the word I'm is 3 tokens and the word hello is just 1 token, that's kind of fundamentally shooting yourself in the foot because it's like every single one of these columns is 80 milliseconds. So there's a mismatch between the like discretization relationship between the text tokens and sentence piece and each token of time, and here where you want everything to be aligned. So that's why they have to introduce these special pad tokens so that if this word happens to be very quick to say but not a lot of tokens, you can add these pad tokens. Okay, let's go back up here. Let's look more about this RQ transformer. The RQ transformer consists of 2 transformer models. So really there's 2 things here. There's a temporal transformer, which is taking VS1, VS2, or you see how S1, S1, S1. So all of these are S1, which basically means they're the same. You see how A1, A2, A3. So S1 means they're all this one here. 1, 1, 1. And then the 1, 2, 3, 4 here, right? The second index corresponds to basically this here, 1, 2, 3, 4. So the second index is kind of like the depth or the kind of height, right? So each separate stream, and then the first index is kind of like the along the time dimension. So this first one is kind of taking all of these together. You see how all of these get concatenated? That's what this little arrows into the plus into this. It basically means you're concatenating all of these together. And then the depth transformer is basically the opposite of that. Now you're kind of consuming the multiple sequences, and really the reason you want to do that is so that all of these can bleed into one another, right? The reason you have these 2 different transformers, one temporal and then kind of one in this height or depth or multi-stream dimension, is so that this token here, this A prime 10-2, can effectively pay attention to all of this shit here, right? It can pay attention to this A12, or it can pay attention to this yellow A58, right? It has the ability, because these are transformers, to pay attention. There's a way for that information to get into this and then allow it to change the probability distributions on the next token that it's outputting, which is ultimately what it needs to do well, right? It needs to get very good at predicting the probabilities for each of those little tokens that it's outputting. So you take your V0 all the way to VS1, you feed it into this temporal transformer that produces this temporal context vector ZS, and then that temporal context vector ZS contains all the temporal context, right? All the kind of like time-based, like here's what was kind of said before, here's the fact that you were angry, blah, blah, blah. All of that compressed into some weird little vector that we don't really fully understand, right? Some d-dimensional vector that contains that information. And then the depth transformer is receiving that temporal context vector along with all the VS1 all the way to VSK minus 1. And that's going to produce your logits estimate, and then your logits estimate is going to be used to pick which of the tokens you're going to output. Depth transformer has 6 layers. So these aren't like super huge. These are like little transformers. Introducing the delay, we already talked about this and how 2 steps of delay at an 80 millisecond kind of frame rate is effectively how they get this 100 millisecond theoretical latency. You can handle overlapping speech turns. That's fine. We already talked about that. 2 streams of audio. A corresponds to Moshi, while the A prime models the user, right? This is what they were saying, where it's actually it can predict the user output. So that's useful because when you train this, right, you can basically generate a conversation and then compare that to the conversation in your data set, right? That's how you're actually getting a gradient. You're getting a loss from the fact that you have data sets of people talking back and forth that aren't even real data sets, right? They're basically fake data sets. They're text data sets that are like synthetically generated using 4 other different pre-trained models and then turned into audio data sets. And because it can output both the user audio stream and its own audio stream, you can push gradients into all of that. But then in practice, you're not actually producing the tokens there, right? Very similar to how when you are autoregressively producing tokens in a language model, like in the actual training, you can output the fake user, but when you're actually doing inference, the model's going to wait to see what you type in, so you get to pick these purple tokens, and then it gets to do these. Can it happen with generated Gaussian splats or games? 100%. That's what I'm telling you, right? Like, doesn't this seem like it? Like, imagine a robotics situation. Even just last week's paper, if you guys remember last week, we were looking at some Gaussian splat papers, and specifically there was one paper where they were like streaming Gaussian splats in these kind of like chunks. You can imagine that being one of these streams, right? So like in a robotic situation, one of these multi-streams could be literally like a chunked Gaussian splat that represents the world. So not only is it outputting action tokens of like, here's what I'm going to do with my little gripper, but it's also outputting like here's what I think the world is, and here are like Gaussian splats that represent effectively the update and the changing world state that I'm living in, right? Yeah, right? Now, Yatharth is feeling the AGI now. As soon as I saw this in this multi-stream, I was like, holy shit, someone needs to do this for robotics. Okay. To integrate. So they're using Whisper to get a timestamp. We define 2 special tokens, pad and epad, that never appear in any of the word tokens. Epad is inserted before the next word to indicate the end of the padding. Oh, so epad stands for end pad. So you have hello, pad, end pad, token, 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 Oshi, pad, 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 and then at some point you'd have end pad, epad. Okay. Inference. All right, I think that's pretty much it for the actual design. So we went through both of these in terms of the design, but now we're basically on the dataset section for both of these. So let's actually look at the datasets for these. So obviously these guys are using basically these instruction tuning datasets, and they're turning them into audio datasets using Cozy Voice 300M SFT. These guys don't have to do as much shit as these guys, right? Because these guys are using kind of a better starting point, right? They're using the encoder and the decoder of Whisper, and they're using the LLaMA 3.1 as the LLM. So the LLaMA-Omni is kind of similar to like a vision language model in that you don't actually need a massive data set and pushing a ton of gradients there, because it's like the LLM kind of already has a bunch of intelligence. The speech encoder and the speech decoder, like those are already pretty good, right? Because the Whisper v3 was pretty good, right? Whisper v3, it's been trained, Whisper v3 large was trained on 1 million hours of weakly labeled audio, 4 million hours of pseudo labeled audio collected using Whisper large v2, right? So here's that same pattern of like previous generation AIs being used to generate data sets for next generation AIs. But right, because those are already pretty strong, you don't need a very complicated data set, which is why these guys can kind of get away with just a 200K kind of synthetic speech instruction data set. Here's something that I thought was weird is in this part of the paper, they have pre-trained spelled 2 different ways. So they have pre-trained with the dash and then pre-trained without the dash. I was like, what? I feel like I kind of use the dash one, but like, I don't know, maybe people like this one. I just thought it was kind of like schizo that the same different spelling of the same concept is used in like within 1 like millimeter of each other, which is kind of crazy. 5 times downsampling, and then it's trained on for NVIDIA L40s, this is kind of one that you don't usually see. So usually you see H100s or A100s, or even if it's like a small research kind of academic paper, you might see like a 3090 or a 4090. But like an L40, kind of a weird one. This is the L40. It's a released in 2022. Four gigabytes, 48 gigabytes. I don't know. I hadn't necessarily seen that one before. And then they basically get the scores using ChatGPT, which is kind of, it's funny that that's basically become the standard where you're using an AI to tell you whether your AI is good or not. So GPT-4o scores content and style, so they have some instruction following benchmark kind of situation, right? Like a fake conversation, it generates the output, and then you're like, okay, GPT-4o, is this good output? How good is the content? How good is the style? And here is them basically showing you that it's state of the art, but they're not really comparing against this one, right? Which is kind of the usual problem that we run into when you have two papers that are basically released around the same time, like, and both of them can claim state of the art because neither of them had access to the other one's thing, right? Like these guys here, when they released the paper, they probably didn't run LLaMA-Omni in their benchmarks because it's like, it didn't even come out until the paper was already done. So it's like, you always have a bunch of papers all releasing state of the art at the same time, and they're only comparing against papers that were released like 6 months ago. So it's like perpetual state. Like lots of people can claim state of the art because they can claim ignorance because the stuff that they should be comparing against didn't actually come out until they already released the paper. They have some other kind of scores here. Mean opinion score, some other random bullshit quantitative thing. This one is a little bit more latency, 226, which I think is pretty good, right? Like 226, let's check it out. Like that's definitely doable. I'm sure talking to some people's grandparents is much higher than 226 latency. That's actually another thing that I'm kind of looking forward to, is that when I listen to podcasts, I've like slowly worked my way up, and at this point, it's like I pretty much only listen to 2x, which allows me to consume a lot more content, but it also, like, I wonder if we're going to have the option to use speech assistants at like higher speeds, right? Like I'd love to be able to interact with a speech assistant that like doesn't talk back to me at 1x because it almost seems like unbearably slow. Like I want something that can talk back to me at 2x or 3x. Right? And then when I start having neural links in my brain, like even higher, right? Pushing the input bit rate to your brain even like higher and higher and higher. And the same way that people can get kind of unreasonably strong by kind of slowly over time lifting weights and getting stronger and stronger and stronger, I wonder if something that we're going to be doing in the future as humans is kind of getting better and better and better at increasing the amount of information that we can get in at one, like instantaneously. So increase your bit rate. Maybe that will be the measure of intelligence, right? Rather than measuring intelligence as like your ability to get a score on a test and know the right answer, maybe intelligence there'll be like, how many words per second can your brain consume before it just can't handle it? Okay. We were looking at the data set for this, and now we should look at the data set for Moshi, because this one's actually even more involved. It's pretty fucking crazy. Okay, they have Wikipedia, Wikibooks, Wikisource, Wikinews, and Stack Exchange. And here's 10 different crawls. So, right, like a crawl is basically like someone went out with a robot and they just scraped all of Wikipedia, right? But because Wikipedia changes, scraping it on 2018 is different than scraping it on 2023. So they're actually using many different crawls of all these different sources. We use an audio collection of 7 million hours, transcribe it with Whisper. So there's Whisper coming back to take these 7 million hours and turn it into text. All the audio is resampled to 24 kilohertz and downmixed to mono. So actually, if you can see here, right, the audio itself is coming in at 24 kilohertz. I think there's a chart here that I can look at that has it. Here's your, nope, this one? Nope. All right, I'm never going to fucking find it. But 24 kilohertz down to 12 hertz, which is 80 milliseconds, right? I think actually the first one has this. Yeah, you see this right here? 24 kilohertz, that's 24,000 samples per second, which is what you get in an audio waveform. And that's not even that high. I think there's like 44 kilohertz. That's like high quality audio. 24 kilohertz is actually in some ways considered low quality audio. So they're taking 24 kilohertz and then turning that into 12.5 hertz. So it's 24,000 samples per second into 12.5 samples per second, and 12.5 samples per second corresponds to exactly 80 milliseconds, right? So that's all the math works out. 80 milliseconds is roughly 12 hertz. Let's go back down to the data set. They have this Fisher data set, which is 2,000 hours of phone conversations between randomly paired participants with a topic to discuss, which is collected in 2004, which is like, that's kind of interesting, right? Like in 2004, someone was collecting a data set of 2,000 hours of fake phone conversations. Like 2004 is like before people really were thinking about like scale is all you need kind of mindset, right? The bitter lesson, kind of like scale is everything. Like that is a recent kind of mindset, right? So having the prescience to collect 2,000 hour phone data set in 2004 is like kind of crazy. Each conversation is recorded on a separate channel, which allows providing ground truth separated streams. This is a big thing. That's probably why this data set is so important, is because the purple and this is separated, right? If you envision this data set, but it was collected on like a single microphone, then you'd have to separate out like who's talking when, right? And because you have to separate out who's talking when, you couldn't do this multi-stream generation, because the Moshi is speaking at the same time you're speaking. It's just speaking silence tokens, right? So the fact that this is separated into two channels is absolutely crucial to their entire multi-stream pipeline. So they got kind of lucky here with this Fisher data set. We use Audio SR to upsample it to 24 kilohertz. So they're taking this Fisher data set, right, which is sampled at 8 kilohertz, which is, right, some crusty 2004 Microsoft XP data set, right, at a kind of a shitty old school resolution. So they have to use an Audio SR, which probably stands for Audio Super Resolution, to upsample it. So like there's so many different, like this data set is so synthetic, right? It's like multiple layers of synthetic on top of each other. It's kind of like ultra processed food in some way, right? It's like you're taking like meat scraps and then like turning it into like the goop inside a sausage, and then taking all those sausages and then grinding them up again and then turning them into some goop that you put into a new sausage, right? It's like they've made the sausage like 5 times at this point. They take 170 hours of natural and scripted conversations and then fine-tune the model to improve the quality over the one obtained when using only Fisher. So they kind of similar to the image generation models, you know, like we read the Stable Diffusion paper, and they had this kind of pre-training on like a lot of data and then fine-tuning on like more high-quality data. They have a similar kind of idea here, right, where you pre-train on kind of like the larger data set, and then you take the time to create a very clean, very crisp, very high-quality data set, and then that's the one that you kind of push gradients with at the very end, right? Like that's the one that has the quality. So this idea of like big messy data and then super high quality small data at the end, that's also seems to be a thing in audio world. They use text-based and structured data sets just as Hermes. Data formatting was often impossible because it's like a written language, right, as opposed to spoken language. So they're going to use Helium, which is fine-tuned on this Open Hermes after it has been turned into audio. So they use a TTS to create 20,000 hours of synthetic speech data. To give Moshi its own consistent voice, we also conditioned the TTS on the voice of a single actor. So they want it to have its voice. To give Moshi information about itself in the QTI, somebody's going to have to tell me how to fucking pronounce that. QTI? QTI. We generate paragraphs describing both of them, and use them as additional context. So maybe one kind of unrelated thing I wanted to show you guys right here is this. So this guy, he's kind of like a jailbreaker dude, but he's mostly like one of the most useful things that he does is he gets the prompt leaks, the system prompts. So I'm not like 100% sure this is the exact system prompt, but you know, it could just be semi-hallucinated, but I feel like this guy's been good before, so I have a somewhat high certainty that this is the actual system prompt for ChatGPT Advanced Voice Mode, but I'm not 100% sure, right? So we don't actually know, but it was super interesting to read through this because it is a little bit creepy. You are chatting, you are helpful, witty, and funny. Do not be overly solicitous. Do not use flirtatious, even if the user asks you. And then this is the sentence that everybody was going crazy over is act like a human, but remember that you aren't a human and that you cannot do human things in the real world. Like, what the fuck? This is where we are at in the AI world, is where we have to tell the AIs not to be human in the secret system prompt. So creepy. Oh, you're saying we should ask the Moshi demo to pronounce QTA? QTA? This paper is very chaotic, too much going on. Yeah, there's definitely a little bit of over-engineering here. You know, like, there's a lot of pieces, you know, like this Archie transformer, I feel like there's a simpler abstraction somewhere there, right? This here, like the separating out into the semantic and acoustic tokens, and then for the acoustic tokens, having this like 8 layers of RVQ here. And it's even more complicated than that because they say here that they have to, let me see. They like specifically talk about having to split out the VQ and the RVQ. Yeah, right here. We propose that this, so while distillation significantly improves the phonetic discriminability of the first quantizer, so this is the distillation from the WAV-LM, it affects audio quality negatively. So they have to separate out and use a split RVQ. So rather than a single RVQ, which is the residual vector quantization with 8 levels, we distill semantic information into a plain VQ and then apply RVQ with 7 levels in parallel. So that's what you're seeing here, right? So here you see how there's actually, in the bottleneck, there's actually 2 separate things here. There's this VQ that is just one level of vector quantization, and that's what's actually being distilled with this WAV-LM, right? So you see this right here, boom, and then here's where your loss is coming from. So you're getting one distillation loss that's pushing in this way, right? It's going in through here, and then it's blah, 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 and it's pushing into here. And then you have a different, this is the 7-layer RVQ, which is split out. And they call this split residual vector quantization reconstruction. So that, along with like this type of shit, I feel like those are gonna smooth out, right? I have confidence that over time we're gonna figure out simpler architectures that are a little bit more adherent to the bitter lesson, you know. But for being a tiny little startup, right? Like we got to give these guys credit. Like, this is like 12 people. They're fucking taking on like OpenAI which has like infinite money. So, you know, it is a little bit over-engineered, but hey, they released like a fucking 60-page paper and it works pretty well. So, you know, you can't be too harsh on them. Okay. Let's finish up the data set. I think we're pretty much done here with the data set, but fine-tune the thing. Here's the language model. Voice adjective includes happy, surprised, examples of characters, generate instructions containing misspellings. So they have to kind of use data augmentation techniques, right? The same way that you would kind of like Gaussian blur an image in order to, or flip the image, or like apply some transformation to the image that kind of like makes it more shitty in order for your image detection model to be robust to shitty images. Here's the same thing, right? They have to kind of create augmentations to their data set that make the audio quality lower so that their model is robust to low quality audio, right? So like if you're talking to Moshi and you're like surfing with Zuckerberg on one of those wave surfer things, right? Like the audio that's going into your phone is going to be so shit that you want your voice assistant to be capable of robustly using your low quality audio tokens. We generate questions containing a false or misleading fact, such as, is the Eiffel Tower in Beijing, to train the model to answer no and correct the user. We generate safety conversations where the user asks unethical or not safe for work questions, and Mochi refuses to answer these requests. I don't know, like, both of these papers, the level of, like, synthetic data generation is high, right? Like, there's so much... Like, these data sets that these AIs are being trained on are like further and further and further from like actual human data. And that's why I don't think there's any limit to this, right? Like, a lot of people, like, for example, like the data flywheel moat. Yeah, so some people are like, if you talk to like a VC or someone like that who's trying to invest in AI, right, they might tell you this flywheel, right, where they have this idea that, like, hey, if we can give you a ton of money and you can make a product that is good, lots of people will use your product. And if lots of people use your product, then you can get more data. And then more data means better AI, right? And on a superficial level, okay, that kind of makes sense, right? More data equals better AI. But is it really? Like, do you really need user-generated data to make a better AI? Because both of these papers, there's no fucking user-generated data here. This is just like these massive synthetically generated data sets based on scrapes off the internet with a Whisper v3, right? It's like, I think this is a fundamentally broken model, right? Like, you don't actually need user-generated data, right? So maybe there's a lot of investment that's going into AI that's based on this idea that you're somehow going to get a moat because you have more users, but I don't know if that moat makes sense anymore, because both of these papers, like, they're getting basically state-of-the-art performance and they don't have any fucking users. They just can create these very complicated synthetic data sets from what's out there already, right? And if that continues to happen, right, if we continue to be able to use Whisper v large v2 to train Whisper v large v3 and then use Whisper v large v3 to create synthetic data to train Whisper v large v4, we're no longer limited by more data and more users, because we can just create all that data synthetically. So I don't know. This is like the paradigm shift is happening. H100 GPUs, everyone's favorite GPUs. TTS training. This is the other half of the Mimi, right? There's the ASR and then there's the TTS part of the Mimi. This one is not using GPT-4 to determine the quality. Here they actually got 20 people to listen to 10-second audio samples and tell you whether it's high quality or not. I don't know. I honestly kind of skimmed through most of this here. Audio artifacts caused by model quantization. Entropy spectrum of a well-behaved sample. Short silences occur naturally in Moshi's output due to the model's multi-stream abilities, reflecting the other speaker's turn. Significant degradations occur at low bit width. These are not always well reflected. So basically, right, you want... Quantization is going to be important for these types of models, because something like a voice assistant like this, right, you're going to want to be able to run this on a cell phone, right? You want to run this on the cell phone. But the cell phone is extremely small, right? It has very limited compute. So quantization, which is taking a model and then representing each of the parameters using lower precision data types, allows you to take a bigger model and then run it at a smaller compute footprint. But much like this fundamental thing here is lossy, quantization is also lossy too, right? As you kind of quantize your model more and more and more, it gets shittier and shittier and shittier. So there's always this kind of like push and pull there of like, how heavily do we want to quantize this before it's just so deep fried that it can't really work well. But I don't know. I think we're close. I think that there's a world where quantization and pruning and sparsity techniques just don't work well enough. And because of that, all the models are run in the cloud, and all the AI that you interface with day to day will be basically running in the cloud. And then there's a different world where quantization and sparsity and pruning work so well that all the AIs that you interact with in the real world are basically just running locally on your cell phone, right? So like there's a fundamental difference there, because in one world, these big data centers will basically be the biggest driver. Like there'll be so much money in the big data centers because everyone's queries are going through these big data centers. All of everyone's data is in these big data centers. That's kind of a creepy Orwellian world, right? Where you basically have centralized control over all the AI that you're using in your everyday life. But in this second world where quantization and pruning and sparsity result in models that are so tiny that you can basically run them on your cell phone, or you can run them on your VR headset, or you can have like a PC in your house that's basically running all the models, that's a fundamentally, I feel like, better world, because now all that data is there locally, right? You're no longer actually sending any of your data to some data center somewhere. It's just staying locally within your little house. So in that world, I think it's very difficult for one centralized power to kind of control anything, because they no longer have a stream of data that's going to them and that they can basically control. So I'm hoping for the small models locally world and not the big models in the cloud world. Okay, I think that's pretty much everything I had for these two papers. What is this? Oh, okay, so I was looking at the actual Moshi code here, and this is their Moshi benchmark. So you go down here, and I thought this was kind of interesting. There's a torch.cuda event here, right? And then torch.cuda.synchronize. So looked it up. CUDA has an event management, which is kind of cool, right? Maybe something we're going to have to start working with. What is CUDA events used for? CUDA streams enable concurrent execution of operations. CUDA events can be used to synchronize tasks with or across streams. Events can signal the host code about the completion of GPU tasks without halting the CPU's execution flow unnecessarily. This allows for efficient overlap of computation and communication between the CPU and GPU. So once you're like getting into this audio world where like you're doing things in like this 80 millisecond chunks, right? Like it's not just the model. It's not like just the stuff in the GPU, right? It's not like just the different operations that are happening in the GPU need to kind of line up, but now you also need to basically be coordinating with the CPU too, right? Because the CPU is what's actually taking your waveform and then producing what's actually taking what's coming out of your decoder and producing a waveform that actually wiggles the speaker, right? That little membrane that is the speaker, and that produces a pressure wave in sound that then travels out of your computer, and then you hear it with your ears, right? So like there's CPU things happening and there's GPU things happening, and you need all of those to be very well timed together for this type of multi-stream design, which is why you're starting to see these event abstractions kind of come in. We got OpenAI Whisper. We got some plenty leaks. We got the Qt. We've got that meme. We've got my little latency timer. Here's WAV-LM. Here's Lucid Brains that we were creeping on. We got our Notebook LM. And then we got the L40. Okay, I think that's all the things I had pulled up for these papers. Let me drink this water. I'll answer some questions, and then we'll do a summary, and then we'll be it. Did you check Hume AI? No, I don't know about Hume. PinocchioSatch.gif. Okay, I think you guys are mostly just conversing. There's not really any questions here. Okay. I think I'm just going to give a summary. Okay. All right, here's the summary. So in today's stream, we were talking about speech-to-speech models, or basically models that consume a waveform of audio and output a waveform of audio, right? And it's called voice mode because I wanted to kind of game the SEO a little bit, right? I figured people might be typing voice mode into YouTube because OpenAI released their advanced voice mode. But we didn't really talk about OpenAI's advanced voice mode. We mostly just talked about these two papers. LLaMA-Omni from some academic Chinese institutions, and then we have Moshi from Qtai, which is a French startup. And these are both basically open source advanced voice modes. They're very low latency, right? They have a latency of basically 200 milliseconds. And they released very extensive papers that show everything that they did, all the different parts of their system, the different problems they ran into, all the different hacks and tricks and tips that they had to do to get this stuff to work. So we got to thank the open source community for making this stuff available to us, you know, because it could have very easily, they could have just never released this and then we would basically be in the dark. But thank God we got these guys because, you know, we can now actually dig in and see how these things are being implemented. So the way that these work, LLaMA-Omni, I would say, is almost like a VLM. It's basically the vision language model kind of pattern. So you have your LLM, you're kind of gluing it to some pre-trained image encoder, in this case, a pre-trained speech encoder, using kind of an adapter layer. You have these kind of two-stage training pipelines where you're first pushing gradients into the LLM and the adapter, and then later into the decoder. Kind of works cool, but the problem with this one is that because the decoder runs in a non-autoregressive manner, it's really just kind of taking each chunk and then producing the words from that. So, or the speech from that little chunk, which I think limits the kind of experience that you can have with this type of assistant. So a slightly more advanced version of this is in this Moshi paper. And in this paper, they actually use what's called an RQ transformer right here, RQ transformer, to simultaneously produce and consume multiple streams of tokens, right? And these different streams represent basically different things. So they're kind of like separated out. You have a text token, which is representing this inner monologue, right? This like kind of like scratch pad that the LLM can kind of pay attention to and look at. Then you have semantic tokens, which is kind of the information content of words, and then acoustic tokens, which is kind of like the sound content of words. And then it's also consuming and generating streams or sequences of tokens for the user conversation and audio. And actually, now that I think about this, one problem with this is that it can only simulate two-person conversations. You actually couldn't do a three-person conversation with this, which is kind of interesting. But, okay. Another, I think so that's the two different designs here, which are actually a little bit more similar, but I think the big story to me on both of these papers is just how they're trained on these synthetic data sets, right? How basically both of these papers took text data sets and turned them into audio data sets and then trained on those. So I think that's kind of a big story here of like, you don't actually need users to create data to create a good AI. At this point, like something like a Whisper v3 is basically a way of infinitely generating audio data. And because we have a huge amount of text data out there on the internet, right, like these Wikipedia scrapes, you can effectively create these very, very large synthetic audio data sets. And then because audio, a synthetic audio is actually much closer to real audio, right? Another way of saying that is the sim to real gap in audio as a modality is actually quite small. And this is maybe not intuitive to people who work in kind of image modalities or video modalities or robotics modalities where the sim to real gap is very big, right? The sim to real gap between a simulated robot with working in like some kind of like Unity like simulation and a real robot, there's a big difference there. But synthetic audio, the sim to real gap is so small that you can actually just create these giant synthetic data sets and then train on it, and it works quite well. So I feel like that's a big part of the story here that maybe will get lost in the general kind of hype that people have just to have a voice-to-voice model. But yeah, that's pretty much it, guys. 2 different open source speech-to-speech models that are released right around the time that OpenAI released their voice mode that basically give you a rundown of what is needed to produce this type of user experience. That's pretty much it, guys. Is it possible to revisit 1.58 mini LLMs? You're talking about the like extreme quantization papers where they quantize all the way down to like 1.58 bits on average. It's not early fusion methods. Yeah, so what Prasuk is talking about is the early fusion is actually, in a way, you could say it's kind of early fusion. Like, what is this? How early is early in early fusion, right? Early fusion means that the different modalities are basically getting mixed together at the lower layers of the transformer, right? Any kind of AI model is multiple layers of transformers. So are you, in this one, this is not early fusion, right? Because your audio is going in and then it's going through an encoder and then it's being turned into this. So like your LLM is taking these tokens here and it's kind of at the end, right? There's all this shit before it. But here, like, how early is this? I guess it's still after the encoder. If it's before the encoder, it counts as early fusion. Is that kind of what you're saying? I don't know. IDK. Hopefully that was useful. If not, I'm sorry. But have a great weekend. Thank you, Sarah, Prasuk, Twan, Sid, Yatharth, MWD, Godbuddy, Zeke, Mind of a Fool, IP, Every Dream, Sid, Twan, Johnny Boy, The Lookerful, Ed, Oma, who else? They Call Me Ken, Majetti, Devin, or Devrim, Daniyal, Ed, Sotaki. Thanks, guys, for hanging out. Hope you guys had a good time, and see you guys next week.